Welcome back, Design Junkies, to Mechanical Engineering Made Simple. Today, we're undertaking a really critical deep dive into the very core of machine design. We're talking about the components that control motion, transmit power, and, most importantly, manage all the stress and longevity.
That's right. Gears, cams, bearings, linkages, the works.
A whole vocabulary.
Our analysis is coming from some seriously dense engineering handbooks. I mean, they focus intensely on the geometry, the manufacturing, and the sometimes brutal calculations you need to make sure these things actually survive.
So our mission today is really to pull out the functional essence of these parts.
Yeah, and to show you why every single moving part is a small, hard-won victory against the physics of failure.
What becomes immediately clear, and you see it right away in the sources, is that it doesn't matter if you're looking at a simple little detent or a, full-on aerospace actuator. The design is just this massive balancing act.
Every millimeter, every angle, every material choice has to be absolutely precise. There's no room for error.
Okay, so let's start with rotational power. Let's start with gears.
The fundamental language of gears.
Okay.
And first, we have to define tooth size. That really splits into two major systems.
Metric and US.
Right. In the metric world, we use what's called the module. And it's actually pretty simple. It's just the gear's pitch diameter in millimeters divided by the number of teeth.
Okay, straightforward enough.
Right.
But in the US customary system, we use the diametral pitch.
And this is one that always trips people up.
Oh, because it's inverse, right?
It's totally inverse. It's the ratio of the number of teeth per inch of pitch diameter. So the physically larger the gear tooth is, the smaller the diametral pitch number becomes.
It feels completely backwards.
It does. But that's just how the ratio works. And that demand for precision, it flows right into the manufacturing process.
You can't just cut the stuff out of a block of metal.
No, absolutely not. To create a gear face that can withstand constant high load, you're talking about highly specialized operations. You need milling, then maybe hobbing for spur gears, or end milling and shaping for internal gears.
And some things, like bevel gears, need their own specialized machines.
Exactly. And it's not just gears. It's astonishing when you look at something like a standard roller chain sprocket.
Right.
They have to adhere strictly to ANSI standard geometry. The dimensions aren't just picked. They are derived from these complex equations based on the pitch, which we call P, and the number of teeth, N.
So every single curve is mathematically defined.
To the thousandth of an inch. I mean, take a half-inch PIX roller chain. The source gives a minimum seating curve value of 0.317 inches. It's calculated down to that level because if that contact point is even slightly off,
You just destroy the chain.
you're destroying the chain and the sprocket. It's a rapid failure, which, leads us right into material selection.
Because the material has to handle those forces.
Precisely. For something low speed, light load, sure, you might get away with engineering plastics, acetyl, polycarbonate, things like that.
But for any serious power transmission.
You immediately jump to heat-treated ferrous and non-ferrous alloys. No question.
And this is where it gets really interesting because this quality, both material and manufacturing, it's all quantified by the AGMA quality numbers.
Yes. And this is where you get just a profound insight into the mechanical hierarchy of the world. AGMA numbers define exactly how accurate your gear manufacturing has to be.
So give us an example. What's the range look like?
Okay, think about a simple agricultural baling machine. It might be perfectly functional with quality numbers between, say, 5 and 7.
Okay, so that's pretty loose tolerance.
Very loose.
Yeah.
But then you jump into something sensitive, like electronic instrument control and guidance systems.
That's a whole different ballgame.
It is. Suddenly you need quality numbers from 10 all the way up to 14. The tolerance just tightens massively.
And what's at the very top end?
Well, if you are engineering something truly demanding, like a space navigation sextant and a star tracker,
Wow.
you need quality number 14 and up. The required accuracy for a mechanism pointing to a star is it's a different universe compared to one compacting hay.
It shows that precision isn't just a cost factor.
No, it's a mission-critical constraint. And that material choice also dictates how you can even machine the part. Machinability is hugely affected by heat treatment.
I've heard that some of the high-carbon steels are just a nightmare to work with.
They are. A 4150 grade steel is notoriously difficult to machine. You have to specify tempering for steels like 4140 just to make them manageable on the shop floor.
And all of this is before the system is even running. Once it is, you have to deal with the operational forces.
Right, which the designers have to anticipate. A simple spur gear will generate tangential and radial loads.
Hmm.
But systems like helical gears, or even more so, worm gearing,
They introduce that third dimension of force.
a massive axial load,
Yep.
thrust. And the calculation for the forces in a worm gear system is where things get really complex.
You can't just use simple geometry.
Not at all.
Yeah.
You have to factor in the coefficient of dynamic friction and the system's overall efficiency. And that complicates everything, especially selecting the right support bearings. Because that friction is what converts the rotational input into a crushing axial load that the bearings have to absorb day in and day out.
Okay, calculating those continuous forces is hard enough, but what about controlling the timing and the specific path of a movement? That's even harder.
It is. And that brings us to the systems that manage selective controlled movements, CAMs.
Right, so cams are what convert that simple rotation into something much more complex.
Exactly. They're defined as mechanical components that convert continuous rotary motion into a specific, predetermined translating or oscillating action using a follower.
And the absolute dictator of which cam profile you choose?
It's speed. It's always speed.
So for low-speed movement.
You might use something called a uniform velocity motion, but this is actually terrible because when the follower hits the flat part of the cam, it goes from zero acceleration to maximum acceleration instantly. It's like hitting a wall. The shock is incredible.
And that shock is exactly what you're trying to engineer out of the system.
100%. Uniform acceleration and parabolic motions are better for moderate speeds because they smooth out that transition. But for any kind of high-speed application, you absolutely must use cycloidal motion.
Why is cycloidal motion the go-to for high speed?
Because it's the only profile that keeps the acceleration curve smooth. The shape is mathematically designed to ramp up and ramp down both the velocity and the acceleration gradually. It prevents those massive g-forces from destroying the follower and, the mechanism itself.
We see that design battle against shock loads everywhere in cam design. I was reading that the slope lines defining the rise and fall have to be terminated with a parabolic curve.
Specifically to prevent shock loads. If you skip that tiny design detail, your follower mechanism will literally hammer itself apart.
It's amazing. Now, there are two main types of follower systems, right? Open track and closed track.
Correct. You have open track cams, which require the follower to be held against the cam surface by a spring. Think of a standard engine valve train.
Okay, so a spring is pushing it back.
Exactly. But then you have closed track cams where the follower actually travels inside a groove. This gives you positive action.
Meaning no spring is needed.
No spring. This is critical in manufacturing machinery because if a spring breaks in an open track system, the whole machine fails immediately. Closed track cams eliminate that specific risk.
But the challenge with the spring-based systems, the open track ones, is what happens at high speeds.
You get spring floating, the spring just can't keep up with the cam profile, and the follower loses contact. It literally floats off the surface.
How do you fix that?
The fix is designing the spring with a natural frequency below the cyclic rate of operation. And often, the solution is to put multiple springs in parallel. That's exactly what you see in the complex valve springs of high-performance automotive engines.
And then on the total opposite end of complexity, you've got the simplest cam of all.
The eccentric cam, the most economical to make. It's often just a round disc that's offset from its center axis.
You see those used for simple rise functions or actuating limit switches and timing devices?
Yeah, but you can't run them at high speed. For ultra-high speed, we have to look at some really advanced systems like the desmodromic system.
This is the system that was famously used by Mercedes-Benz racing engines back in the 50s.
It actually used a second cam to physically force the follower back down. It completely eliminated the need for springs.
So if you ever hear a high-revving 1950s Grand Prix engine, that really distinct mechanical clatter.
That's the sound of springs being completely engineered out of existence. It's the noise of pure positive mechanical action.
Amazing. Now, when you're designing these cam profiles, there are other constraints too, right? You have to look at the contact interface.
Oh, absolutely. The geometry is critical. You have to make sure the roller radius is smaller than the minimum radius of curvature along the cam profile.
Otherwise, you'd actually cut into the cam itself when you're manufacturing it.
You'd undercut it. And you also have to calculate the contact stress, which we call S sub S. For a material like SAE 4340 steel, heat treated to Rockwell C50, the max allowable compressive stress is 220,000 psi.
220,000 pounds per square inch.
Yep. And if your calculation exceeds that stress limit, you have designed a fatigue failure point. It's guaranteed to break.
Okay, let's shift from cams to linkages, the building blocks of movement.
We all remember the 6 basic simple machines, but we're focusing on mechanisms that translate motion in really ingenious ways.
And maybe the most dramatic is the toggle joint linkage.
This thing is just incredible. It's a mechanism designed specifically to multiply force massively. As the linkage angle approaches 90 degrees, the mechanical advantage and the velocity ratio both approach infinity.
That's a trick of geometry.
It is. The classic examples are the bolt lock action of the Luger pistol or, giant rock crushing machinery. Both use the toggle to generate thousands of pounds of crushing force with a relatively small input.
Then you have the 4-bar linkage, which is just everywhere.
Absolutely ubiquitous.
Yeah.
Just 4 links connected by 4 pivots. You see it in everything from car suspensions to construction equipment.
But it looks so deceptively simple.
It does, but mathematically, its action is extremely complicated. Before the 1950s, figuring out the precise motion for all points was often just trial and error. You'd build a prototype and see what it did.
It wasn't until the mathematician Freudenstein developed his geometric relationship that designers had a really robust mathematical tool.
That's right. But even then, the sheer difficulty means that mathematical solutions are often approximations at best.
Which is why, even today, high-speed motion analysis is so critical. You have to actually film the prototype.
Exactly. You watch the complex actions happening at 12,000 frames per second just to confirm the mechanism is performing the way you thought it would.
And this analysis has its own defined vocabulary. You see these letters, R, P, and S.
It's a kinematic vocabulary. R is for a revolute joint, which is just simple rotation. P stands for a prism joint, which allows sliding. And S is the sphere joint, your classic ball joint.
And these designations let engineers define these incredibly complex three-dimensional mechanisms.
They do. But then there are some linkages, like the RSSR linkage, that just defy the standard rules of kinematics.
The Maverick space mechanisms.
That's what they're called, because they achieve this complex non-standard motion that you just can't analyze using basic planar geometry. They're a class of their own.
All right, so all of these moving, complicated parts, the gears, the cams, the linkages, they all have to be supported. Which brings us to part 3, bearings and the science of precision fits.
Let's start with the simplest type, the plain bearing, often sintered bronze.
And their selection comes down to one critical calculation.
The PV calculation, the pressure velocity factor. P is the pressure on the projected area, and V is the surface velocity. And designers have to balance these.
And this balances everything. You can't just max out all the values.
No, you can't use the maximum for all 3 simultaneously. If you run your machine at a super high velocity, you have to lower the load. If you don't, the bearing material will simply melt or disintegrate from the frictional heat.
It's a hard limit.
A very hard limit. For example, lead-based Babbitt has a maximum PV of 35,000. But PTFE fabric, a more advanced synthetic material, only has a limit of 25,000. These material limitations directly constrain how fast and how heavy your machinery can possibly be.
Then we move up to rolling element bearings, your ball, roller, tapered, and cylindrical types.
Here, we're relying on authoritative bodies like the Anti-Friction Bearing Manufacturers Association, the AFBMA, for standards on load ratings and fatigue life.
And this is where the cost of miscalculation just becomes brutally clear.
It does. There are 2 critical approximate rules for bearing life that every single engineer has to know. The first one is this. Doubling the bearing load reduces bearing life to 1/10.
1/10, not half. 1/10. That is a monumental penalty for a small increase in load.
It's huge. And the second rule is just as important. Doubling the speed reduces bearing life to 1/2.
So controlling load and speed isn't just about performance.
It's about controlling the maintenance schedule, the downtime, the entire life cycle cost of the machine itself.
This sensitivity brings us to maybe the ultimate constraint in all of mechanical design, the precision fit. The fit of a bearing into its housing is often the last and most critical step.
It really is. The U.S. customary classes of fit range from RC1, which are close sliding fits just for accurate location,
All the way up to FN5.
which are the heavy force fits, used for parts that are designed to be highly stressed and never ever move again.
Let's use an example, an RC3 precision running fit on a 1.5-inch nominal shaft.
The tolerance window required is just incredibly narrow. The shaft and the hole have to be machined to clearances that are often less than 0.002 of an inch across the entire diameter.
That's tighter than a human hair.
Tighter than a human hair, across the whole part. If you miss that tolerance by even a fraction, the shaft will either seize up from heat expansion or it will vibrate itself to pieces. immediate fatigue failure.
And for the tightest connections, the interference or force fits, you have to calculate the stresses.
You have to. Designers must treat the parts as thick-walled cylinders to calculate the internal stresses. This determines how much torque can be transmitted and the axial force you need to physically press them together.
And the stress analysis is absolutely critical here.
Because the maximum tangential and radial stresses happen right in the contact surfaces. Designers have to use stress concentration factors, maybe 1.5 to 2.0, especially for thick hubs pressed onto a shaft. If you neglect those factors,
You risk a sudden brittle fracture
yeah,
or a catastrophic fatigue failure somewhere down the line.
absolutely. So our deep dive today has moved us all the way from the generalized motion of gears through the controlled linear action of cams and linkages, and finally into the critical support systems defined by bearings, these hyper-precise fits.
The complexity forces designers to master combined disciplines. You can't just be a mechanical engineer anymore.
You can't. You have to understand mechanical, electrical, and electronic systems.
And that really is the ultimate insight. When you look at modern electromechanical products, whether it's an industrial switch assembly or a high-precision titanium camera shutter, it demands that engineers become general practitioners.
Yeah, you have to grasp all three disciplines rather than sticking to a narrow specialty. Precision in one area requires mastery in all the others.
And this complexity brings us right back to the limitations of pure analysis. We discussed how incredibly difficult it is to mathematically solve the precise motion of something like a 4-bar linkage.
And that difficulty often forces modern engineers to rely on computer-aided design and critically physical dynamic analysis.
So here's the final thought. When you look at any complex machine operating smoothly today, an engine, a robotic arm, a printing press, anything, ask yourself this.
Are the specific movements you are watching the result of elegant mathematics that perfectly modeled the entire system from the start?
Or were they finely tuned by watching a prototype's slow-motion video captured at 12,000 frames per second, with engineers correcting the geometry based on observed physical reality?